3,100 Kelvin. Now that is a jaw-dropping temperature. To put that into perspective for you, it's actually hotter than the boiling point of a lot of common metals, and yet this is just the melting point of an unsung industrial superhero. We're talking about a material that quietly, behind the scenes, makes modern civilization possible.
So, welcome to this explainer on magnesia. You might also know it as magnesium oxide, or just MgO. Today we're really diving into the research to uncover the secrets behind this absolute workhorse of extreme industrial environments. So let's jump right in. Here's the roadmap for today. 1. The ultimate industrial superhero. 2. Origins, mining and seawater. 3. Superpowers and kryptonite. 4. Building armor, engineered composites. 5. Forging the modern world. And finally, 6. The future of magnesia.
All right, kicking things off with Section 1, the ultimate industrial superhero.
Magnesium oxide is what we call a refractory oxide ceramic, and brilliantly, it shares the exact same simple crystal structural blueprint as regular old table salt. You know, that standard NaCl-type structure. But here's the massive difference. MgO has highly charged magnesium and oxygen ions sitting in that lattice, and these create such intense ionic bonds that they impart a massive cohesive energy. It actually boasts a lattice parameter of about 4.21 angstroms, which means its atoms are packed incredibly tight, and it has a massive enthalpy of formation. Essentially, that just means it takes extreme energy to build it, and it's incredibly chemically stubborn to break apart.
Moving on to Section 2, Origins, Mining and Seawater.
Now, you might think a material like this is exclusively mined. And yes, the Earth does hold up to 13 billion tons of magnesite ore reserves, mostly in places like China and Turkey. But, thanks to the industrial Dow process, we can actually pull off a really clever chemical trick. See, our oceans contain about 1,300 parts per million of dissolved magnesium ions. So by adding lime to seawater, we can literally precipitate pure magnesium hydroxide, or brucite, right out of the water. Then, we calcine, or fire, that solid to yield pure magnesia. It's an absolutely brilliant, renewable source of this critical ceramic.
As you might guess, extracting magnesia is a highly endothermic process. It requires massive amounts of heat. And basically, the hotter we fire it, the denser, pure, and less reactive it becomes. Take caustic calcined magnesia. That's fired up to 1,000 degrees Celsius, and it remains reactive. Meanwhile, dead-burn magnesia is fired way past 1,500 degrees to become incredibly dense and stable. And then at the absolute extreme, you have fused magnesia. That's melted in electric arc furnaces above 2,500 degrees to achieve the highest possible purity and these massive single crystals.
But here's the catch. Pure MgO is notoriously difficult to sinter and densify. Other ceramics usually form this liquid, glassy glue at their grain boundaries to bind together when heated. Pure magnesia doesn't have that glassy film. So to close those microscopic pores, we have to rely entirely on extreme heat and solid-state diffusion. It requires multi-step firing, and we have to be incredibly careful with impurities. Things like silica or iron can form weak secondary phases that compromise the entire structure, and we absolutely need maximum strength here.
Which brings us to Section 3, Superpowers and Kryptonite.
Heavy industry is completely dependent on magnesia, and it really comes down to these numbers. It melts well over 2,800 degrees Celsius. It's a near-perfect electrical insulator, boasting a resistivity greater than 10 to the 20th power ohm meters. Plus, it has a room temperature compressive strength between 1 and 2 gigapascals. That means it can support massive physical loads, even at extreme heat. But its true superpower? Its basic chemical nature makes it highly resistant to aggressive calcium-rich molten slags. Acidic silicates would dissolve other ceramics like alumina on contact, but MgO, it just brushes them off. But of course, every superhero has its kryptonite. First up, thermal shock vulnerability. Magnesia has a relatively high thermal expansion coefficient for ceramic. If you cool it too quickly, those massive thermal stresses cause it to crack and shatter. Second is hydration risk, and the irony here is actually staggering. A ceramic forged at thousands of degrees in an electric furnace will expand by 33% and literally crumble into dust if it just sits in a humid room and absorbs moisture. It's chemically reverting right back into brucite. Let's look at how we fix that in Section 4, Building Armor. Engineered composites. To build a virtually indestructible material, engineers rely on the industry standard MgO carbon brick. By mixing about 80% magnesia with 15% graphite flakes and 5% resins and antioxidants, we get an incredible composite. The rigid magnesia grains are essentially wrapped inside this flexible, interconnected carbon skeleton. This carbon matrix gives the brick what's called pseudo-ductile failure. That means it can flex just a little bit rather than shattering, which grants it unbelievable thermal shock resistance.
But there's a strict trade-off happening here. Carbon's armor is perfect in many ways. It repels basic slags, provides extreme toughness, and conducts heat brilliantly to prevent that thermal shock. However, carbon's weakness is oxygen. Above 600 degrees Celsius in regular air, the graphite literally oxidizes. It burns away into carbon monoxide and dioxide gas, leaving the brick totally porous and weak. And that is exactly why we must carefully add chemical antioxidants, like silicon carbide, to protect the armor itself. Aside from carbon, engineers have designed some other totally ingenious composite armors to solve very specific problems. For instance, MgO spinel composites lower the overall thermal expansion and resist alkali corrosion perfectly. MgO mixed with zirconia adds transformation toughening, which actually absorbs energy to stop cracks from spreading in high-temperature crucibles. And MgO combined with silicon carbide forms protective forcedrite layers that block oxygen intrusion. We are essentially customizing the microstructure to fit whatever danger the material is facing.
Okay, Section 5, Forging the Modern World.
So where does all this go? Well, the vast majority of this super material effectively vanishes right into heavy industry. A whopping 70% of global magnesia usage is devoured by the steelmaking industry alone. It acts as the sacrificial, ultra-high temperature lining in basic oxygen and electric arc furnaces. Another 10% lines the massive rotary kilns used to produce cement, while the remaining 20% supports glass manufacturing, foundries, and aggressive chemical processing plants.
And this really brings us back to that microscopic basicity we discussed earlier. In basic oxygen furnaces, MgO perfectly resists the aggressive iron oxide-rich slags that make mass steel production possible. In cement rotary kilns, it survives harsh alkali vapors and dusty calcium silicate melts without even flinching. In glass float tanks, MgO blocks maintain the furnace volume against highly corrosive lithium, sodium, and potassium silicates. Its chemical resistance is quite literally the bedrock of our global infrastructure. Finally, Section 6, the future of magnesia. The evolution of this material is happening as we speak. Right now, the focus is on perfecting ultra-high purity fused MgO to raise its resistance even further. But within 5 years, we're looking at 3D printed refractories using binder jetting. Imagine being able to print an entire furnace block with internal cooling channels perfectly integrated. And in 10 years, AI-assisted design will analyze specific industrial slags and immediately predict the absolute perfect MgO to spinel composite ratio to combat it, all while integrating nanostructured MgO to enhance strength and catalytic properties.
And here's why this matters so much right now. Heavy industry is scrambling to decarbonize. Because of magnesia's unique heat capacity and its reversible hydration properties, remember how we talked about it absorbing water to become brucite? It is currently being developed for high-capacity thermal energy storage. It's essentially acting as a massive thermal battery. Furthermore, MgO-based sorrel cements are being engineered to actively capture CO2. Magnesia is officially pivoting from a passive brick into an active green technology.
So, it leaves us with a pretty incredible thought. Could the secret to completely decarbonizing heavy industry be hiding in the atomic structure of a simple seawater-derived ceramic? It's a fascinating possibility to consider. Thank you so much for joining this explainer today. I really hope this encourages you to look a little closer at the invisible, extreme temperature materials that are quietly holding our modern world together. Keep learning, and I'll catch you next time.